about RL and public policy, which is maybe not a space that you've heard about too much before. And I should say this is sort of work that's done with a bunch of co-authors and collaborators. And I'm supposed to caveat that like all the views I'm expressing are my own and not of any federal agency or any of my co-authors or any company. And so we've heard a lot about reinforcement learning successes in the real world. AlphaGo is used to pilot real weather balloons. It's used to do chip layout design. I saw an article the other day that it's being used to train F-16 fighter jet AI, and it's been used to fine-tune 175 billion parameter models. And then yesterday we saw, nuclear fusion. And so I want to come back to the fighter jet example because it's sort of relevant because it's in the government setting. And we'll talk about that a little bit at the end. And so the federal government has been investing heavily in AI throughout every federal agency and obviously in the military as well. And so there's a lot of investment going on and a lot of promotion for the use of AI to sort of make government more efficient. So I want to talk about where does RL fall into this spectrum of public policy and government work. So first I want to talk about what makes for a good RL and public policy problem. Then what are the areas of public policy and government services that can be improved with RL? And what are the unique research challenges in that space? And then how do we feel comfortable safely deploying something in these settings and whether RL should be deployed in these settings? So first, what makes for a good RL problem in public policy? Not everything should just have RL thrown at it, right? And so it should have an environment that changes over time. You need to both explore and exploit. And you maybe should probably have to plan ahead. Though if you consider like contextual bandits to be RL, which some people do, maybe you don't need to plan ahead all that much. And so what are the areas of public policy and government services that can be improved with RL? So we actually see a lot of sequential decision-making problems in the government. And so there's a lot of enforcement. So for example, the Environmental Protection Agency has to audit condensed animal feeding operations to make sure that they're compliant. And so really that's a sequential decision-making problem. Recent work has actually used active learning with satellite imagery to help the EPA audit CAFOs. The Internal Revenue Service audits taxpayers for compliance. And actually that's a sequential decision-making problem, and I'll talk a little bit more about that later on. The Brazilian government audits regional governments for corruption. There's a recent work using machine learning to figure out which regional governments to send resources to. And generally, all of these are resource allocation problems, right? And so there's more of those problems throughout government settings, COVID-19 test allocation, and even the Delaware Department of Transportation has been thinking about using RL for traffic control. And so there's a proposal to actually use that in the real world. And so what are the difficult challenges when you're thinking about RL for public policy? So there's sort of an explosion of challenges as soon as you take on one of these problems. And I made, maybe a little bit of a kitschy little figure here of, the Big Bang. As soon as you take on one of these public policy problems, you have to deal with all the requirements of the agency, all the sort of policy setting requirements. You have to have noisy data, small data. You have, batch selection that you have to do with delayed rewards. And so there's all these problems that normally in research we take on one at a time, but here they often come at you all at once and you have to sort of handle everything all together. And so I want to zoom in on multi-objective decision making, which is actually a really big feature of pretty much every public policy problem. And so you may not know, but every sort of enforcement agency at the federal level has to abide by certain reporting requirements. So there's a bunch of bills, and I should say I'm talking mostly about the US government, but generally, this sort of applies internationally as well. But so many enforcement agencies have to they both have to figure out where to, allocate enforcement resources to find the most instances of misreporting or fraud or what have you. But they also have to give an estimate back to the government and say, how much do we think is how much corruption is out there, how much fraud is out there, and they have to get statistically valid estimates of that, which typically means you have to randomly sample, right? And so if you're setting up an RL problem in this space, what you actually have to do is you have to balance the random sampling need for the statistically valid measurement and the RL problem. And so we actually collaborated a bit with the Internal Revenue Service, and I should say once again, these are not my views, not the IRS's views, and all of this work was done on secure government laptops, and I was a student volunteer at the IRS to do this work, so everything was very secure, and this is all my opinion. Okay. You'll learn if you work in public policy, you have to make a lot of these statements. Okay, so why does the Internal Revenue Service do audit selection? Well, the tax gap is measured at $441 billion per year. So that's the difference between the amount of paid in taxes and the amount that people should have paid in taxes. And so there's estimates that if you invest $1 into better targeting, better IT, you get $10 back out of that $441 billion gap. And so how do they balance currently the estimation problem of estimating that $441 billion number and figuring out where to send auditors? So right now what they do is they have two programs. One, the National Research Program, which is 15,000 audits per year. That gives you the tax gap estimate, with a lot more special sauce involved, obviously. And and then they use that 15K random sample to train a risk model with a few other internal selection mechanisms, and then they use that for operational audits. And so you have these two distinct systems. You can sort of think about it a little bit like epsilon greedy sampling, right? You have your epsilon sample and then your greedy selection. But it's really an RL problem, right? You have an environment and an agent that has to make selections, and then the environment is changing every year, and you're continuing to do this loop, right? So if you're smartly reusing information, you can actually improve this process and improve that multi-objective problem. And so basically, you have the state, which is all the tax returns that you can audit in a given year, with everything in a tax return as the features. Your agent has to both make an estimate of the population reward and select the next audits to sample. Underlying the environment, there's structural changes to the economy, there's tax code changes. Once someone gets audited, everyone in the network is less likely to misreport. So there's a lot of changes going on behind the scenes. And so, and then your reward is once someone gets audited from your selection, the difference between the amount of the difference between the amount owed and the amount paid, the adjusted amount, is your reward. So it's basically what you recovered from auditing the person and identifying the tax misreporting. And these rewards come back maybe 1-2 years later, sometimes even longer for really complicated returns. So there's a significant delay, and you have to figure out how to deal with that delay, which is a little bit unusual for RL problems. And so what we actually did is we looked at how do we balance the multi-objective problem, how do we balance misreporting identification with the estimation problem. And so what you want are unbiased estimates, right? And so you really need some sample throughout that risk distribution. And we bucket the risk distribution into bins, and then we sort of have a lever, a hyperparameter that lets us configure how much are we willing to trade off in terms of that random sampling, and we bias it as much as possible toward that higher part of that risk distribution while retaining statistically valid estimates. And this gives you an ability to sort of figure out how much you're willing to give up in terms of reward to maintain your solid population estimate. And we actually find there's a bias variance reward trade-off because to have that unbiased estimate, you give up some variance in the reward estimation problem, and you might have to give up some reward because high reward estimates can also be high variance. So future research can investigate how to navigate this trade-off better, maybe reuse information to better improve services. So this is sort of the done with the IRS setting. So what do we learn from these sorts of challenges is that public policy and government services applications have a lot of really difficult problems to navigate. And that makes for really interesting research challenges in RL. And then, in turn, if we solve those, we can help improve government services. It sort of, makes government more efficient, allows more allocation for beneficial social spending, things like that. And so, but how can we feel comfortable deploying these in, very sensitive contexts sometimes? And so often the case is that many of these services are already sequential decision-making problems. And selection is just not formalized, right? So there are many cases where you're better off formalizing the problem and understanding these trade-offs and figuring out how to navigate these trade-offs appropriately. But as we've sort of seen in many of the talks, evaluation is a hard challenge, right? And to sort of make sure that you're formalizing properly and not being overly confident in a deployment, you need to make sure that you have really thorough evaluation. And so I want to talk about another government setting from, a long time ago now at this point, but there was some slides that were leaked that basically said that the NSA is using random forest to train on 7 positive labels to identify, so-called couriers as part of their Skynet program. And so this is obviously an extremely severely underpowered evaluation, right? And when you're evaluating RL algorithms, you need to think about, what is the statistical power I need to actually feel confident that I'm deploying something appropriately. And this was obviously not an appropriate deployment. 7 labels is just not enough for anything. And so we really have to be careful when you're working in the public policy space, when you encounter problems where simply you just don't have enough data and it's just not appropriate to deploy, you need to have appropriate safety measures and stop signals to say maybe not. And so there's a lot of work in sort of safety in RL and proper evaluation, bias fairness audits, and causality checks that really should go into these pipelines to think about when you should or should not deploy something. And so if we have better validation, we can build trust and confidence, equity and safety, true efficiency, not just sort of perceived efficiency, and we can put in place appropriate fail-safes and red lights to sort of stop when things aren't working appropriately. And hopefully that leads to better public policy and government services and sort of better all social good. But you sort of have to stop and think about what you're doing, right? And so that brings me back to the fighter jet example. As we've seen earlier, there are many cases when RL algorithms do something that we don't understand. They come up with a solution that seems good, but we don't really know why, or maybe it's doing something that's really not good if you look at it long term. And so when you have deployments in government settings especially, but overall throughout both private and public sector, it's really important to think about what you're doing and take a step back and think, if my RL algorithm fails in some unexpected way, is it really going to cause significant harm? And I think this is one of those cases where, if a fighter jet has an RL algorithm and we don't know why it's behaving the way it is, maybe we should take a step back and think, how can we verify that before putting it out there where it can really cause some significant harm? And so that's something that maybe people don't think about as much in RL because it's not deployed in these settings as often, but as governments get ready to gear up and deploy such algorithms, we really need to take a step back as researchers and think about the things that we're working on and the implications for downstream deployments, and make sure that you validate things as you publish, because really when you publish things, people look at what you're publishing and they will see those evaluations and take them for granted. So it's really important to thoroughly vet everything you're doing because public policy in RL is a thing. So thank you, everyone. And